Good afternoon. I'm pleased that there's still a good crowd here. It's a real pleasure to introduce our first speaker this afternoon. Is going to be, the English pronunciation is Jacob de Zoete. Okay, the Dutch pronunciation is
Jacob de Zoete.
There you go. Okay, so apologies for getting it wrong. Real pleasure. And I actually spent last weekend reading Jacob's PhD thesis, which was a great pleasure. And I'm sure this talk's going to be a really good continuation of that.
Thanks a lot for the introduction, and also thanks for the organizing for inviting me. As Dave mentioned, he was just reading my PhD thesis. I've been a PhD student with Marjan for 4 years at the University of Amsterdam, and I've handed in my thesis, but I still need to defend it. So although on the program it says Dr. Jacob de Zoete is not doctor yet. So today I would like to discuss some recent work of mine, which is on generating Bayesian networks in forensic science. 3 years ago, when I was visiting Dave and Norman in London, we worked on some serial crime and Bayesian networks for serial crime. And recently I've worked on packages that can assist you generating these networks for given situations. So today the goal of my presentation should be that I first introduce a Bayesian network structure for crime linkage problems. I will apply this to new situations and furthermore show you how computer assistance can aid you in getting networks for other situations. And later on, because the focus shouldn't be on the crime linkage problems themselves, but what you can do when you use a computer to generate these networks, I will suggest some other ways in which I believe a computer can assist in understanding or working with Bayesian networks. So as a first example of a serial crime situation, there is some burglary. 1 week, and there is some evidence there. The week after, there's another burglary, which follows a similar modus operandi. There's other evidence there, and the suspect is apprehended shortly after the second burglary, and he becomes a suspect because he matches the characteristics of the evidence in 2 cases. So, first of all, some sort of a disclaimer here. So there, obviously, when you would like to model such a situation, there are numerous variables that influence the probabilities of interest, and which essentially means that a probabilistic approach is never complete. You can always come up with, well, is this evidence discredible? Shouldn't we account for this? I do not really agree with this number. So I do believe that the Bayesian network can always be improved, or a probabilistic model can always be slightly different. But on the other hand, a probabilistic approach is definitely more informative than just following your intuition, and hopefully it will come clear in this talk. The most important message of this slide should be that I will show some posterior probabilities, but do not see them as something that you report in court, like, well, apparently with 98% he did it, so let's convict him or not. It's more, it gives you the indication of how the dependency structure works together and how we can learn from these networks. Okay, so essentially in crime linkage situations, for this case 2 cases, there are 3 questions that you need to consider, namely who's the offender in case 1, who's the offender in case 2, and is there a common offender in these cases. And these 3 questions work together, for example like this. So if you know that the offender in the first case is the suspect, and you know that there's a common offender, then you also know that the suspect is the offender in the second case. And that's sort of the, sorry? Okay. Either way, so this is sort of the intuition when doing crime linkage. But you can also do it in a more probabilistic way. So you have a similar model. You have some initial belief. Again, do not focus on the numbers themselves, but see it as a low initial belief that the suspect is the offender. And then you look at one case, like how likely is it that the suspect is the offender in this case. And for the example that I suggested, there was the evidence consisted of a hair was found at the crime scene, and there was a shoe mark supposedly left by the offender. Then we have our initial belief that the suspect is the offender, and we insert evidence which gives us a posterior belief that the suspect is the offender. So again, there are some numbers here, but they're not the most important. So if we would introduce this reasoning for this one case here, then we have our prior belief that the suspect is the offender. We put the evidence in for the first case. We put the evidence in there for that there's a common offender, namely the similar modus operandi. And we get a posterior belief that the suspect is the offender in the second case. So this is just a probabilistic way of doing the intuitive approach we showed before, or I showed before, where you would completely sure.
May I just make a quick comment there on what you just showed?
A very quick comment, yes, sure.
The result is the product of the 90% and 90%.
No, not exactly. No, almost. So let's not go into this discussion. But this number is correct, and you should read the paper later on, and you understand why it's slightly different.
It struck me there was a potential implicit assumption that the proposition about being the same and the proposition about being the suspect are independent of each other, and there is no conditional linkage between them.
I think that should jump into a subject that's not really relevant at this point. So numbers are correct, and you can talk to me afterwards if you want to know the specifics. So if we get some probabilistic reasoning for this case, but now if we actually look at the evidence, then we have in the first case we have a shoe mark and a red hair, and then there's the same modus operandi, a shoe mark and the finger mark. And we can distinguish different types of evidence. So this evidence is relevant for the first crime, this evidence is relevant for the second crime, and we have evidence that's relevant for the question whether there is a common offender. But actually there's also evidence that there's a common offender in the shoe mark evidence, because if you see the same shoe mark on both crime scenes, or the same size at least, then this suggests that there is a common offender. So that brings us to sort of four types of evidence that we distinguish here: for the first crime only, for the second crime only, for the link between crimes, and a sort of a combination for a specific crime and the similarity between crimes. And all of these are in the structure that I suggest, a model slightly different. Well, you will see that. So we have the overall thing, then we have the evidence for the first crime, the evidence for the second crime only, the evidence for the link between the crimes, and you have the evidence that's specific for both the first crime here and for the second crime here, but also for whether there is a common offender. So this shows the structure that I suggest for these crime linkage problems to get a hold of how the dependency structure works in these situations. Okay, so sort of an intermediate conclusion. With this probabilistic model that sort of contains the most important uncertainties in terms of the evidence, we have made a probabilistic model for the situation we have. Now this structure can also be adapted to new situations, like we could add another case, we could add other evidence. And also with this model you'll be able to get some posterior probability for the culpability of a suspect. And this is just representing your change in belief and not necessarily a true value, because we have a simplified situation of the actual case. So let's look at these posterior probabilities for this situation. So we start again with some 1%. This is already a simplified graphical representation of the actual network, but I think this captures all the relevant information, just so you know. So we include evidence, like there's a loop pattern in the finger mark in crime 2, the hair was red, there was a similar modus operandi, and we put in the shoe size, a size 46, which is kind of big, and we have the posterior belief. So this shows that we can actually make some computations with these networks. So as said, most importantly, we have identified 4 different types of evidence that play a part in modeling these crime linkage situations, and we can add new cases or new evidence to expand this network. Say that another case would come up, but also we can apply this structure to another case, and that's what we'll do now. So say we have another example. This is a sexual offender who is lurking in the forest, and maybe there are more, maybe there's only one, and 2 weeks after each other someone is attacked in the forest, and the week after an undercover agent goes in on a bike, because that's important, and well, it's actually not, but the offender is captured in that case. So we are sure who's the offender in the third case, and apparently the suspect matched with the shoe mark and the Y chromosomal DNA profiles that was the evidence in the first 2 cases. So we can again only focus on the evidence that we have here. So I've just highlighted the evidence, because that's sort of the idea here. You look at the evidence and then you determine for the evidence for what question is it important, because that determines how we should model this in the structure that I suggest. So we have the Y chromosomal DNA profile, which is relevant for the first crime. Oh, this should be second crime, I guess. Yeah, sorry, so these two should be over here, and these two should be over here. Either way, you understand the underlying idea. And with this table, which also includes the modus operandi, we can follow sort of the recipe to make a structure for this situation. So we have the offender in case 1 and the evidence that's there. We have the offender in case 2 and the evidence that's there. Case 3, where there's evidence that he was caught red-handed, so that's quite strong. And we have evidence that there is a common offender. And now we can draw the arrows between the relevant questions and also the necessary edges between the evidence. And now it's already...
yeah. The same offender has to be in all 3 cases, couldn't be in just 2 of them.
No, yeah, so that's for example what I mentioned with that this is a simplified graphical representation of the actual network. So this actually contains of multiple that says, is there a common offender between 1 and 2? But good question, but it's sort of for the visual appeal of it, I summarized in this one. So we can come up with this one, and again we can do the computations. Also, you see here that whether there's a common offender is less likely, because here I use the state that they're all the same. So before it was only 1%, but now it's lower. So there you sort of see this this question in the graph itself. So we can insert the alleles that we've observed, and we can insert the modus operandi that was in the common forest, and we get new posterior beliefs. And once again, it's just to show that following this recipe, you can come up with a network that allows you to compute posterior probabilities in terms of how does the evidence work together, what is the dependency structure. Okay, so I'm going quite fast, I guess. So what I tried to show here is that for a new case, we can follow the same recipe, we can look at the evidence, determine for what question the evidence is relevant, and that determines how we should model the case itself, and we can repeat this procedure for any situation. However, this was still quite simple situation with only 3 cases with little evidence. But you might be interested to applying this to a bigger case with more cases, and then it becomes practically complex to fill in the conditional probability tables because they're quite big to make sure that the network structure is correct. So that's why I suggest to generate networks for these situations. So this is the third example and the last example in terms of these crime linkage situations. So now there are 6 cars that set on fire in some small village. There's evidence that there's a common offender because the same type of gasoline was used. There is different types of evidence. I think they have CCTV footage that shows that the arsonist had black hair. There are finger marks, there are shoe marks, there are DNA profiles. So lots of evidence, lots of cases. And again, a suspect is found wandering around the scene of the crime. And this person matches all the evidence found in the individual cases. So here it sort of highlights the evidence that we have again. And I made up here what evidence was in what crime, but say that you have something like this. So you have evidence in crime 1, crime 2, crime 3, crime 4, and then the rest of it. So here this is all the evidence that suggests that there's a common offender, which has to do with whether you saw this evidence in multiple cases. So CCTV is found in 2 cases, whereas a finger mark was only observed in the first crime, so there's no evidence that there's similarity with the type of evidence finger mark. And here this coincides with where the evidence was found. Okay, so we could, well, in practice or in theory, actually, we could make these network ourselves. So we have offender in case 1 with the 3 types of evidence, offender in case 2 with the 2 types of evidence, and so on. And you get this structure, and now it becomes quite awkward to fill in these probability tables because, for example, this one has, I think, 5 parents, the CCTV node, and the same offender node captures many states. It's not just there is a common offender, but is there a common offender in 1 and 2? Is there a common offender in 1 and 3? So if you have to do this by hand, it will take you lots of time, and you probably make some mistakes along the way. So it's sort of summarized in this slide that even in this case you can follow this recipe, but the effort or the time associated with doing this becomes infeasible in practice. Furthermore, it's likely that you will make some mistakes along the way because these probability tables are massive. But both problems would disappear when you use a computer for both of these tasks. So this is, it's quite, maybe we can turn the light down here, maybe that's slightly better, or is it sort of readable what it says? Well, you will see this later on, I guess. There is sort of suggestion I have. So you put in the number of crimes, you put in the number of evidence types, you put in the number of possible offenders, which sets the prior probability for all the states. Again, you might argue that that's not a sensible thing to do in a real case, but here it's more as a computational tool or to sort of scrutinize your reasoning. This is not for reporting posterior beliefs, or at least I would vote against it. The random match probability, or this is actually the likelihood ratio of the involved with first evidence, and whether the type of evidence was observed in the first case. So now I would say, well, there are two crimes, and you have a similar structure on the left, and you would get this network. And this is all put into a computer. More importantly, I've used a R package called grain, which allows you to use Bayesian networks in R. And furthermore, there is a web application framework, which is also a package called Shiny, which allows you to build standalone websites based on your R code. So you can, and I did, put this online, so you would be able to go to this website, or this for the shorter URL, and you can make the network yourself based on the different situations. So you can say, I have this many crimes, you have this many potential offenders, there is this type of evidence and then that crime, and these are the random match probabilities associated with these types of evidence. And then you can play around with it or download the network yourself, which gives you sort of a real-time option to evaluate the evidence for your given situation. And that's particularly comes handy, I think, in a sort of a, for example, at the Forensic Institute, when you're interested in, so what am I dealing with here? How does these pieces work together? And just to understand the situation better, and once again, not for computing posterior probabilities that are sent out to court and saying, well, we used the web application by the Zoete, so you can try it again and convict the guy. Furthermore, I did this for crime linkage problems because I really like the structure that we've worked on a couple of years ago for crime linkage. I think it's a neat way to model these situations, and I think it's well fit to be put in such a structure. But I think that the most important message I have for this talk is that you can think of other situations where you have these Bayesian networks, and you can actually make this framework yourself, or you can ask someone who's more familiar with R or with grain, with Shiny, to do it for you. So here, as an idea, I've put this whole situation online, which now covers a maximum of 6 cases, just because it's more of a it should give some insight in what you can do with these things. And I can put in all the evidence, so that the arsonist had black hair, that there's a loop pattern size 41, and I get the probabilities. So it sort of combines the R code that I wrote with like Bayesian network software packages like a GNRISC of Norman and Martin, or Eugen, or Genie, or whatever you want, or even you import it again in R, to come up with these posterior probabilities and to get an idea of what you're dealing with. Okay. And before I'm going to go really quick. Well, Marjan will have some extra time. So this is one example that you can do with this. But I was discussing this with Dave the other week, and I mentioned you could think of other situations. You can think of a network that you already agreed upon, but you just want to see what happens if I alter the probabilities a bit. So I played around with it a bit, and I made an alternative example which just shows you what else you could think of, and probably people have other suggestions, and I would love to hear them. And this sort of relates to the talk that Sjerps was giving yesterday, I think it was, where you sort of agree on a structure, but you're interested in what happens if the probability of H, or the probability of transfer, is higher or lower, or we're interested in the persistence, and you can sort of immediately see what happens to the posterior probability, because I think that the drawback of using these awesome Bayesian network software packages is that it takes some time to get familiar with them. So during my PhD I was often at the Netherlands Forensic Institute and we worked on Bayesian networks, and I was quite familiar with building Bayesian networks. Other people were familiar with the answers they wanted out of it, or they were familiar with the evidence or how it works together. And then often we could come up with nice solutions and I could present them something, but it still required them to be familiar with, for example, in Eugen, I have to alter this probability in these 4 nodes and then go back, I have to run the model, and then I get a posterior probability, and I believe I should see what happens if this is 0.7 or 0.6, and it requires some effort, whereas with these solutions you would be able to just alter probability, see what happens, and try to get a hold of what's going on. So a probabilistic model is usually better than just following your intuition in terms of understanding the problem and be aware of whether your intuition is correct. In the paper that is on the crime linkage problems that I did with Dave and Norman and Marjan, one of the important results was that some things can become quite counterintuitive, especially in more complex situations. However, the effort of constructing these networks becomes, I think, infeasible after a while because they're too big, and not only the one who makes the network needs to be familiar with the software packages themselves, but also the users have to be familiar with them. And I think that can be taken away by implementing it in a computer. And that's actually the final line of this final conclusion section. So just as a summary of the 3 things that sort of tells you what to do. So if you want to do exactly what I did, you should read this work, then implement it using these 2, and push your own website, which is slightly better. And then I'm out of ideas because you have a better version. Thanks for your attention.
Norman, you've got a question?
Okay, so you kind of implied it at the end there, but maybe you want to say a little bit more about what you call the counterintuitive stuff, and in particular about the impact, for example, when there's some supposed linked crimes and one of them is actually dropped from the investigation.
I could tell a bit about that because that's the work I did on this paper that's together with Dave, Norman and Marjan. So there we sort of introduced this structure, which was based on an approach by Ian Effett and Graham Jackson, I think DJ Murray, I got the 4th name. However, there we started to putting this in Bayesian networks because it's a problem well fit for Bayesian networks, and there we were looking at what happens if you add a 3rd case and what is there exculpatory evidence in the 3rd case. And one of the important results that we got is that although people might be intuitively drawn to removing this 3rd case from the series of crimes, this is actually can lead to a severe overestimation of the evidence in the other crimes, because as you saw in the examples that I gave here, is that you have crime-specific evidence in one crime, you have evidence that relates to crimes, and that increases your belief that the suspect is the offender in another crime, because you have these 2 pieces. That's like the first 3 questions that I did show on the slide, where you have strong belief there, so it alters your belief here without seeing evidence there already. So I think that was a really nice result, but for this talk I was more focused, because I think there are people in the audience that have seen me talk about crime linkage before, and it gets a bit boring maybe. So this is another take on a similar story, but captures a message on what can we do to improve the results we get from Bayesian networks, and how we can sort of move towards actual users instead of the people that are interested from an academic point of view. But thanks for your question. Yeah.
I have some technical questions. One, if GRAIN is an interface to Eugen or Jena, or it's an independent Bayesian network software?
GRAIN?
Yes.
That's a package for R. So it is R is the software package.
No, I know.
Yeah. So GRAIN is just a package for R, like any package. You download the GRAIN package, which allows you to, I think, conveniently work with Bayesian networks from within R. So it's just a package.
It's easy.
It's not an independent software package. You download R and you say I want to have GRAIN, and you get GRAIN, and it's within R.
Everything is there.
Yep.
But there is something different. For example, you always use a Jena or Eugen, I also do, but sometimes if you have parameters which change with continuous, it's much better to use other kind of software. For example, I use a lot of OpenBars or JAGs and so on. So there it's easier when you have continuous variable, and for example, instead of doing a sensitivity analysis, you can just put a PDF on some of the parameters of interest, and then the macro chair does everything, and you see the distributions.
I think the other software packages are also able to work with distribution, but yeah,
But this is a pain.
yeah. Well, the different packages have I think drawbacks and are better for some tasks. And although I do most of the Bayesian network stuff in R now, I do think that the combination with the actual graphical user interface with a dedicated software package comes in handy, because you get sort of the graphical overview instead of looking at some computer code. And specifically for users, it's nice to see the actual thing and maybe play around with it a bit. But probably there are other packages, yeah. Okay.
Can you go back to the first Bayesian network that you plot?
The
Because
first Bayesian network.
that's the simplest one.
Okay, yeah.
Because there is an asymmetry in the way you construct that. Yeah. So there is, for example, there. So there's two shoe marks.
Yeah.
And without undermining what Phil said at the very beginning, the arrow from the first shoe mark goes to the second shoe mark. But it could be the other way around.
Indeed. Yeah.
And I see kind of an asymmetry in these.
Yeah.
It pops out like it could be exactly the other way around. Is there any reason why you put this way, or?
Yeah, there is a reason, and you're right. You could do it the other way around. And actually, there is a master student from the ETH in Zurich that came up with sort of a structure that is symmetric. But I decided to do it from left to right because I thought it seemed to make sense. Is you first have case one and then you add another case. So you've already seen this, but you could do the other way around. You could also come up with a symmetric approach. But this, yeah. Okay.
Does it matter in which order in time the crimes happen? Maybe that's how you order the events and where the arrow goes from.
No, well, I numbered the cases from 1 to 2. So I thought, let's go from 1 to 2. But that doesn't really matter. I think I've had many discussions about this, and I don't really care about the direction of the arrow. But for example, the way I present it here is that you first see case 1 and then we add case 2. But it doesn't really matter in what direction the arrow is.
But it doesn't matter at what time different cases happen, if you know the time of...
What do you mean with whether it matters?
Well, if one happened yesterday and another one happened today, it's important.
It might affect what you look for.
Yeah. Well, you could have the case where the offence which occurs later in time was the one which was reported first.
Mm-hmm.
And the investigation into that led to the discovery that a similar offence had occurred at an earlier date.
Yeah, of course, but I don't really get why that would be. Then I call one and the other 2, or I just use this symmetric approach. It doesn't. I don't think it would matter in what order you find that, because eventually, if I would make the network, I wouldn't wouldn't figure out which one came first. And, there are 6 cases. Let me do this. So it wouldn't really matter.
It could affect the manner in which the investigation for data took place.
Yeah, obviously, but then you move into
the second one occurred earlier. That the situation is now older than it was. Some evidence may have disappeared.
Yeah, but then we really discuss like how should the prosecutor deal with crime linkage cases, and that's not part of this research. So probably they should do it in the best way they can, but it doesn't really matter how you model it eventually. There might be evidence missing because this one was like 2 months ago, but yeah, I'm not solving crimes.
If each one was investigated on the day on which it occurred,
yeah,
you do not have the problem of aging of data.
But this has nothing to do with aging of data. If you want to do it correctly, if you want to do sort of a model of crime linkage in a correct way, then probably you collect your data on the day of the crime or at the same moment. But
if you can.
Yeah. So if I would talk to a police audience, I would tell them, hey, you should do it on the day that it occurred, and even if you're in bed, just go out. But now it doesn't really matter because it's about the model.
Yeah, well, it could be that the actual reporting of the crime to police. I mean, say you're talking about damage to cars. Yes.
Yeah.
The owner of car number 1 was away on holiday.
Yeah.
And only discovered the crime when he came back home.
Yeah.
Which was after the second crime occurred.
Yeah.
So that would be a case where the earlier crime was reported later for good reasons, nothing to do with the police.
But how would that alter this? I mean, yeah.
It could be important for your link, for example, from one shoe mark to another if there was a big stone in between, and it could affect...
Or whether there is a link because you do not find a shoe mark. Yeah, okay, that can affect this, but yeah, absolutely true, yeah. I haven't included notes yet whether owners of cars on a holiday or whether it's a storm, but that might be one for a later version.
Yeah, sure.
Yeah,
Typical.
that would make it more complete, I
You can
guess.
put it in your program at Generate. You can increase
Yeah.
the number of.
It checks like was there a storm in the
Yeah,
city.
yeah.
But I think the people seem to be once again misinterpreting your arrows as some kind of important directionality. They're nothing of the sort. They're just probabilistic conditional tables.
Exactly.
It doesn't matter which way that arrow goes. It doesn't relate to time, doesn't relate to cause.
Why don't you put an arrow either end of it then?
Exactly.
Because
No, because that's not what the technology does.
but
There's a formal semantics for doing this, and this is it. Don't change it.
Even if
But
it's
sometimes if you change just the arrow and the other arrows, you will actually change the structure.
Yeah, but
So we have to be careful about that.
in
might
this
allow-
particular case,
Oh, in this case.
it doesn't matter. I mean, we're arguing about something that doesn't matter.
no, well, I could allow for a function on the website where you can decide that the arrow goes the other direction or the arrow becomes a nice flower. It doesn't really matter.
Imagine there was a big storm and now he has to wear a different kind of shoes because now it's really wet and there is a lot of water.
Yeah, but then you go into detail whether you should use these networks specifically like this in actual caseworks, and that's like what the first slide was about. This is a simplification of the problem, but indeed, with specific case circumstances, you might be inclined to remove this arrow because shoe marks have nothing to do with each other for some reason. Yeah.
Well, and also you would distinguish between the evidence which is found, like the mark, and have a not observed variable, which is the shoe which was actually
That's missing.
worn.
Or okay, yeah. Well, you could include anything.
Something it could be necessary to put something much more complex.
Yeah.
Those two things
Well,
there.
the way I implemented this is that you get this simplified version of your network, and often in situations I'm interested in, I should add something like witness credibility that Martin was talking about, and that's not yet I think it will be part of the actual thing online, but that's the moment you get the bigger thing and you alter your crime specific information like with small notes, but it takes away like 80% of the effort for constructing it.
Yeah. Any other? Oh, Bill.
Yeah, I just wanted to say, I think this is quite important. When I've looked at actual cases that come up in court, I think this question of the probative value of multiple offenses and trying to link together offenses and so on, and assessment of modus operandi is an issue on which I think my sense is that people have a lot of difficulty thinking this through in a logical way. I do think people probably overvalue superficial similarities between crime when assessing modus operandi. I've seen this phenomena you mentioned where there'll be a series of crimes that look like they could be by the same person, and then there's one where it doesn't match the suspect, and therefore, then it must not be part of the series. And so there's this kind of backward reasoning that goes on in the whole process. So this strikes me as an area where intuitive human judgment may very well lead us astray often, and therefore this kind of modeling might be helpful. It might be worthwhile to think about actually doing some research comparing intuitive human judgment about these kinds of cases with your model as a way of kind of teasing out what kinds of things can go wrong with people's intuitive process of reasoning, as a way of sort of informing the court about a potential fallibility of human judgment.
Yeah, I completely agree with you. We discussed this together the day that we should do this, but I shouldn't be the one that leads such a because that's not my area of expertise. And but if you're interested, I would be nice to collaborate on that. Yeah.
Do you ever test your models against real cases and then that have come up with a verdict and you don't know about it, and then you can test your model against the actual outcome?
I have like in a real case, like a serial crime case, and then put in the evidence. No, I did not, but
Might be a useful exercise.
yeah, I guess so. But
But also an impossible one.
Yeah,
how would you ever know what numbers were put by the fact finder into anything?
But you could do sort of an idea of the number. You could see whether, I think like what Bill mentioned with leaving out a crime, that's something that you can just compare. Like, is it reasonable to do so? And you put some numbers. You don't really care about the exact value. But like, let's try 0.8 and just see whether the reasoning that they use that they could leave out this crime make sense given these numbers, and maybe we should alter them a bit or see to what extent they do really matter and whether they're not. So you would be able to.
Well, you could not consider any numbers, but just be given the information that the original worker had,
Yep.
and then test your own methods, and then test your outcomes with those that were found by the court.
Yeah, but for the outcomes, you need some numbers. The outcome can be just the graphical structure, but that's not something you can compare, I guess. But you have to come up with some numbers to compare their outcome with my outcome. So I think it would be interesting to sort of compare actual cases and the reasoning that was involved in that using such networks, but also be kind of careful with saying immediately after, so you were wrong because my model says otherwise, because probably they took into account
I
stuff
don't
that's...
think you could say right or wrong. It's just nice to test models.
It's also nice to say that people are wrong. So it's,
So your model gives a probability, but in the real case it could be 1 or 0. But if yours say 90 and everyone else said, innocent,
yeah,
your model's
that's
wrong.
quite interesting. At
Or
least
literal.
yeah, you
Or
might have reason to look into it a bit more. Yeah, I agree.
Any other? Okay, so let's thank Jacob.